Hello and very welcome. My name is Dr. Lucas du Plessis. I'm a senior lecturer in the Department of Mechanical and Aeronautical Engineering at the University of Pretoria, and we are busy with the Postgraduate Dynamics module with the acronym msd780. In today's lecture, which is lecture 5, we will be looking at Professor Nick Ravesh's application examples. So just to explain that in a bit more detail, as you already know, we are using the textbook Planar Multibody Dynamics, the second edition, which Professor Nick Ravesh from the University of Arizona wrote, and Professor Nick Ravesh also developed the so-called body coordinate simulation program coded in MATLAB. As part of this simulation program, there are a few application examples that the user can run, and these examples are also explained in the textbook so that the user can understand how the program works and what the functionalities and capabilities of this simulation program are. Okay, so in today's lecture we will look at two of these application examples, namely the double A-arm suspension as well as the McPherson suspension. Okay, so let's dive right in. The double A-arm suspension, it is explained in subsection 8.1.1. This example, as shown in figures 8.1a and 15.6a, is the planar representation of a double A-arm suspension system, where its detailed description and corresponding data can be found in section 15.6 in the textbook. And we will look at section 15.6 in a minute. Okay, let me first show you what the schematic representation looked like. It's the same schematic representation used for both figure numbers. Alright, so subsection 15.6 explains the double A-arm suspension in a bit more detail. One of the most commonly used independent front and rear suspension systems in automobiles is the double A-arm, also known as double wishbone or short long arm. As a rear suspension, the system provides an up and down motion of the wheeled assembly with respect to the frame. As a front suspension, in addition to the up and down motion, it allows a steering degree of freedom. When the system is viewed from the front or back, it exhibits planar motion as a 4-bar mechanism, and this you can see in the schematic representation on the screen. The steering or tie rod does not have any effect on the planar motion of this system. So the multi-body system shown here in figures 8.1a and 15.6a is referred to as a quarter car representation, which could be either the front view or rear view of a car. So Professor Nick Ravesh assumes that this is the frontal view of the left front suspension. Now, for modeling purposes, the joints and the attachment points are labeled in the shown schematic view of figures 8.1a and 15.6a. In this presentation, body 0 is the frame. Okay. Bodies 1 and 3 are the lower and upper arms respectively, and body 2 is the wheel assembly. The wheel tire combination is shown in scaled size in the background for reference. The coil-over shock absorber, that's mounted here between points F and E, is a suspension spring damper. The individual body components of this system and corresponding dimensions are shown in figures 8.1b and 15.6b, and this is the figure you can also see now on the screen. The mass centers of the three moving bodies are G1, G2 and G3. There's G1, there's G3, and there is G2. the mass and roll moment of inertia, the characteristics of the spring damper for the suspension, and the spring damper data in the radial direction or vertical direction are listed in table 15.5. Okay, so here you can see, even though body 0 is the frame fixed to ground, the mass and inertia properties are still shown. The moving bodies, obviously there we do need the mass and moments of inertia of each of those bodies. The suspension, free length, stiffness, damping, all of those information is provided, as well as the tire, the undeformed radius, the deformed radius at rest, the radial stiffness, and the damping coefficient. Right, so the model assumes that the main frame of the car, body 0, is stationary. The moving bodies are indexed 1, 2, and 3. Okay, and this is now, if I can just go back quickly, this is now again on this schematic over here. Okay, so body 0 is the main frame of the car, and that is stationary. Moving bodies are indexed 1, 2, and 3, and we can have a look at the input file in bodies.m. Okay, so what you see on the screen is the function in bodies.m, and here you can see the three bodies, the three moving bodies are listed here. Mass and moment of inertia of each body is also populated. Okay, and we will look at the initial positions and initial orientation of each body in a short while. Okay, so a non-moving frame is defined on ground in a conventional location on body 0. Okay, this is the location of the non-moving XY frame. Before we go on, 3 body fixed frames are defined with their origins at the mass centers as shown here in this schematic figure 8.1b and 15.6b. Now points 1 through 11 are defined at the attachment points of the revolute joints, spring damper, and point of interest C on the wheel. Let's have a look at the input file in points.m. Right, so point Q1, point Q on body 1 is this point over here. Okay, and it is on body index 1, and here you can see the local coordinates of that point Q on body 1. Same goes for point A on body 1. Local coordinates it ties up with what is shown on the screen. Point A on body 2, exactly the same as all the other points. We just have the body on which the point sits, as well as the local coordinates of that point in that body. Point B on body 2 is the same story. This is this point. Point B then on body 3 is also stipulated. Point 03, this is point O on body 3. This is this point over here. Okay. Point O on body 0. This is obviously the one on the frame, point O. Point Q on body 0. This is the point Q over here. Then point E on body 1. That's obviously coincides with the C of G, the center of gravity, and that's also where the local coordinate system is positioned. Okay, and that's why the local coordinates of that point E is 0, 0. Then point F on body 0, that there it is over there. Okay, and then we obviously list all the points, and it's important to take note of the sequence of points. Okay, but we'll get to that in a little bit. Alright, and there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 points. Okay, so the 11th point is actually listed here in the input file in animate.m. Okay, C2 is listed in exactly the same manner as all the other points in the input file in points, but it is in the inanimate file where it is specified. Okay, so once again we've got it as a C2 is a point structure. The body index is body 2, and the local coordinates of point C in body 2 is then stipulated, and we list points anim. There is only a single point C2 that gets listed here. Okay, so the spring damper is represented by a point-to-point force element, and this is shown here in the function, or this is stipulated in the function in forces as force S1. You can the manner in which a point-to-point force is stipulated is using the letters PTP, point to point. It is between P point index 9 and point index 10, and what you can see here is the actuator force. There is no actuator force, it's only a spring damper. So the spring stiffness is stipulated, the undeformed length, and the damping coefficient. Okay, and this ties up with what we had. Here we go. This ties up with what we had over here. The free length is 0.23 meters. Stiffness is 90,000 Newton per meter, and the damping coefficient is 1100 Newton second per meter. The model also requires a non-standard point-to-point force element representing the radial force of the tire to be active only when the tire is in contact with the ground. Okay, and this is specified here with this force S2. Okay, so, and here you can see the type is a user force, and what that allows you to do is there's another input file here, user force, okay, with which you can activate or deactivate the force. Alright, so to determine whether the tire is in contact with the ground, we compute the parameter delta equals the y component of body 2 minus the undeformed radius of the tire, R0, where R0 is 0.35 meters. Okay, so delta is the body 2, the y coordinate, or the second component, minus the undeformed length of the tire. Okay, and this is now forces to undeformed length. Okay, and if delta, okay, and this is what we're saying here, if delta is greater than 0, the tire does not contact the ground, and therefore no tire force is applied to body 2. However, if delta is less than 0, which is stipulated here in the MATLAB input file, then the tire force is computed as a point-to-point spring damper vertically attached between point C and ground, and the force is applied on body 2. Okay, so let's quickly have a look here. A point-to-point spring damper, and here you can see the spring stiffness multiplied by the deformation of the spring plus the damping coefficient multiplied by the y velocity of body 2. This gives the force in the y direction. Okay, so there are the two components of this spring damper force: 0 in the x direction minus Fy in the y direction, and bodies 2 dot F is then the sum of whatever of all the externally applied forces on bodies 2 plus this calculated spring damper force. The model assumes that at initial time the wheel is not in contact with the ground. For the moving bodies, we must provide initial conditions on the coordinates and velocities. Okay, and that's defined in the input file in bodies.m. Okay, and we'll have a look at those in just a short moment. The initial conditions must satisfy the constraints at the coordinates and velocities. If we are not certain that the provided initial conditions are correct, we should ask the program to correct them for us. Since in this model it is assumed at initial time the bodies are at rest, all the velocities are simply set to zeros. Alright, and we'll look at the initial conditions in just a little bit when we look at the details of exercise 8.1. So the exercise asks us to use the following set of initial conditions for the coordinates, and of course the angles must be defined in radians. Okay, where phi 1, okay, R1 is given in meters, the x and y for body 1, x and y coordinates of the center of gravity of body 1, the orientation of body 1, and here you can see it's 357.9 degrees, or we can say minus 2,1 degrees. And that equates to minus 0,036 radians. And the same, I've computed the radian equivalent of each of these angles, and that's shown here on the screen at the moment. Okay, so it asks us to execute the simulation program DAP, which stands for Dynamic Analysis Program, for 1 second, and then observe the animation. And we also have to plot the y coordinate of body 2 versus time. Okay, so let's just quickly show how we entered the initial position of each of these bodies, and there you can see 0,4398 in the x, 0,2512 in the y, and the initial orientation is minus 0,0367 radians, which is listed over here. The same for body 2 and the same for body 3. Okay, and then the initial velocities are 0, and without specifying any velocities, the default that the simulation program assumes or uses, the default that the simulation program uses is 0. In other words, each body standing still at the initial time step. Okay, so let's quickly run the simulation. In order to do so, we go to command window, we enter the word clear, and we also clear the command window, and then we type in the letters DAP. The program asks us which folder contains the model, and this is now the folder AA. Do you want to correct the initial conditions? Okay, so it's a better practice to do so because the initial conditions that we've entered are rounded numbers. Okay, so if you ask even though you might know that those rounded numbers represent the correct initial conditions, it's still good practice to ask the simulation program to correct the initial conditions. So we will say yes. Okay, and there you can see the initial positions X and Y and initial orientation of each of the three bodies, as well as the initial velocities all being 0. Then it asks for the final time step. Okay, and the final time step is 1 second, so we can enter 1. You can ask or you can select a reporting time step, and let's do 0.01. Press enter, and there the simulation runs. Okay, we then type in the word or the letters ANIM, which is an abbreviation for animation. Okay, we click in the command window and press a key, and there you can see the movement of the multi-body system. Okay, the exercise then asks us to plot the y coordinate of body 2 versus time. So in order to do that, we run or we enter the word post, which is an abbreviation for post processing. Okay, and then we can say plot capital T, comma R, open the bracket, colon, comma, and we are looking for body 2, and we are looking for the y component, which is also 2. Close the curly bracket or round bracket, close the round bracket, enter. Okay, let's see what that looks like, and there you go. Okay, so the y coordinate of body 2 starts at 0.35 and then settles at approximately 0.32. Okay, so let's look at the solution that's presented also in the textbook and explained. So here Nikravesh just repeats what I said earlier. Since these coordinates satisfy the position constraint, there is no need to ask the program to correct them. However, if we ask the program to correct the coordinates, we should get the same results back, okay, which is indeed what happened. The animation clarifies that there are no constraint violations at the initial time, and the plot of the y coordinate of body 2 versus time is also shown here in figure 8.2. Okay, and the plot reveals that the center of the wheel drops from a height of 0.35 meters and settles then at approximately 0.32 meters. Okay, and that's exercise 8.1. Let's look at exercise 8.2. Now it asks us to use the following set of initial conditions for the coordinates. So they are different from the initial conditions for exercise 8.1. Okay, so let's quickly do that. Okay, so in order to do that, we will comment out the previous initial conditions and we will uncomment the new ones. So x1 0,51, y1 0,82, as you can see here, and the initial angle is 340 degrees that we convert now to radians. Okay, and the same for body 2. And the same for body 3. Okay, we save the input file. Exercise 8.2 asks us to execute the dynamic analysis program without correcting the initial conditions. Okay, it then says, alright, so let's just do that quickly. So we will, in the command window, we clear the workspace, we clear the command window, and we say DAP, and we say the folder is AA. Do you want to correct the initial conditions? No, we don't want to do that. Okay, it gives us a warning, redundancy in the constraints, but let's just carry on for the moment. We'll look at that shortly. Set the final time to 0. This will evaluate the equations of motion for only t equals 0, and then animate the results that contain only one frame. And it asks us to look at what we observe. Okay, so the final time is 0. We then animate. Okay, so what we observe here is the fact that all the constraints are indeed violated. You can see that clearly if you look at, or if you remember the animation of the exercise 8.1 that we showed a few minutes ago. All the joints were actually connected, and in this case the joints are not connected. Okay, so let's just have a look here at the discussion. Okay, we observe that all of the constraints are violated. The bodies are separated at the pin joints as shown in figure 8.3 and the figure we just shown previously. Now, we may simulate the model again, but this time we should ask the program to correct the initial conditions. Okay, so let's quickly do that. Alright, so we can say clear DAP AA. Yes, we want to correct the initial conditions. The final time is 1 second, 0.01. Okay, and there it goes. You see, now we don't have any warning messages of redundant constraints. And we can animate. Okay, and for completeness sake, let's run the post processor again. And let's plot T, R, body 2, the Y coordinates, close the bracket, and there you see. Now this looks slightly different because we had different initial conditions that we specified. The tire, or the Y coordinate of body 2, actually now starts at a value of, we previously the Y coordinate started at 0,35 and settled at 0,32. Now it starts at 0,24 and it once again settles at 0,32 as before, which is obviously reassuring. So the initial condition corrector that Prof. Nikravesh coded into his dynamic analysis program is successful in ensuring that the position and velocity constraints are not violated. Okay, so that's then the AA arm suspension system, which is the first application example that we looked at. Let us now consider the McPherson suspension as described in subsection 8.1.2. So this model is the frontal view of a McPherson suspension system and is shown also in two schematics. The same schematic is shown twice. It's numbered 8.4 and 15.7a. Okay. The detailed description and corresponding data for this model can be found in section 15.7, which we will look at next. Now, another common type of front suspension systems in automobiles is the McPherson strut and link. The fundamental principles of this system are very similar to those of the double A-arm suspension. Variations of this basic strut and link can be found in different automobiles. So when the system is viewed from the front or back, it exhibits planar motion as an inverted slider crank mechanism. The steering rod does not have any effect on the planar motion of this system. For modeling purposes, the bodies and attachment points are labeled in the schematic presentation shown here that you can see on the screen. So we've got once again the frame of the car labeled as body 0. We've got body 1, 2, 3 and the attachment points labeled as O rather, Q, A and B. And then we also have a point C here that we are interested in monitoring. Alright, so let's quickly have a look. In this presentation, body O is the frame, or body 0 rather. Body 1 is the wheel assembly. Body 2 is the lower arm. And the coil-over shock absorber that includes link 3 acts as a sliding joint or a cylindrical joint in 3D. The dimensions of the links and positions of the attachment points are given in figure 15.7b. Now the mass centers of the three moving bodies are G1, shown in the schematic over here, G2 and G3. Point B is defined on the strut axis at a convenient location as a reference point for some of the dimensions. Okay, and this ties up with this coil over shock absorber that includes link 3 that acts as a sliding body, and I'll show you in a little bit how we use the coordinates of points B and A to define this sliding joint. Alright, so the mass and moment of inertia of the bodies, the characteristics of the suspension spring damper and the tire spring damper data in the radial direction are all listed in table 15.6. Okay, so as before, for completeness sake, the mass and inertia, moment of inertia of the body is also listed here, but really since it is fixed to ground, that does not come into play. The moving bodies, on the other hand, the mass and moment of inertia of each of those bodies do come in play and need to be specified. Alright, so this, the suspension free length, stiffness and damping are all listed here, and the tire undeformed radius, deformed radius, radial stiffness and radial damping are also all listed here. Now, similar to the A-arm suspension system model, we perform a simulation with this model from an initial state where the wheel or tire is not in contact with the ground. Nick Ravesh constructs 3 different models for this system, demonstrating how to take advantage of composite joints for reducing the size of the model. The model, or the three models, contain 3, 2 and 1 moving bodies respectively. Although these models are constructed with different number of bodies and joints, they are kinematically identical. In other words, they will move, all the models rather, move in exactly the same way. And you will see that in a short while. Okay, so let's look at the three models. The first one is McPherson A. The individual bodies and defined points and unit vectors of this model are shown in figure 8.5. Okay, and now you can see that points B and A are used to define the unit vector along which this sliding joint between bodies 3 and 2 are defined. Alright. This model consists of 3 moving bodies. Body 1, body 2 and body 3. 3 pin joints or revolute joints or hinges or rotational joints, depending on how you want to define them. Okay, so there's a pin joint between point Q on body 0 and point Q on body 2. There's a pin joint between point A on body 2 and point A on body 1. And then there's a pin joint also between point O on body 3 and point O on body 0. Okay, so those are the 3 pin joints. And then there's one translational joint that connects bodies 1 and 3. And for that translational joint we will use the unit vectors indicated here with a dashed line and with an arrow over there. Okay, but we'll get to that in a minute. Okay, this model represents 9 coordinates. Okay, each body has 3 coordinates, so there are 3 bodies times 3 is 9 and 8 constraints. Okay, so let's just count those constraints. Each of the pin joints represent 2 constraints. There are 3 pin joints, so 3 times 2 is 6. And the translational joint also represents 2 constraints. So 6 plus 2 equals 8. Okay, the spring damper representing the tire is once again modeled similar to that in the double A-arm suspension model. Okay, that we discussed a few minutes ago. Alright, so let's quickly look at exercise 8.3. Now review the input M files for this model and simulate its dynamic response for 0,4 seconds. Okay, there's nothing strange in the input file in Animate, just the limits of the animation screen, and we'll confirm whether those limits are actually well selected once we run the animation. Okay, so the input files in bodies, there are 3 bodies. Each body has a mass and moment of inertia as stipulated in that table that we showed earlier, and then Nikravesh populates the initial positions and orientations of each body also in this input file. Okay, alright, so we did not have to create a CAD model of this file, of this mechanism, and measure the coordinates, etc. If you create a model on your own and you want to run a simulation, you need to know what those initial positions and orientations of each body are. Okay, because you need to specify those. Alright, and as we saw with the double A-arm suspension, depending on the initial positions and velocities that you specify, when you correct the initial conditions, it finds a solution where close to the positions and orientations that you specify, and that satisfies the position and velocity constraint equations. Alright, so it is important, and this is the point I'm trying to make. It is important what values you enter here. You cannot enter just any random value. It must be close to the configuration that you want to start the simulation of your mechanism in. Alright, so okay, in forces. Right, so let's quickly have a look. There's a point-to-point force between point index 2 and 4. Okay, so to understand that, let's quickly have a look at point 2 is point B1, point B on body 1, and point 4 is point O in body 0. Alright, so if we want to have a look there, let's just have a look here quickly. Yes, that makes sense. So B in body 1, which is correct. This is body 1, and O in body 0. Okay, so there's a point-to-point force between those 2 points. The stiffness, initial length, and damping coefficient are as defined earlier. Okay, and then there's a user force which represents the tire, and this is exactly the same as before. There's once again a stiffness, an initial length, and a damping coefficient. Okay, and this is, let's just have a look here. So it's exactly as before with the double A arm. Okay, we calculate this parameter delta, which is the y coordinate of body 1, okay, minus the undeformed length specified in forces for force 2, okay, and if this delta is less than 1, then we calculate the force Fy, and that obviously takes into account the spring stiffness, the deformation, the damping coefficient, and the y velocity of body 1. Okay, the spring damper force has 0 in the x direction, and minus Fy in the y direction. Bodies 1, yeah, so we just add this spring damper force to the externally applied forces acting on body 1, and then there's also a moment that we need to take into account. Okay, so this S rotation is the way that Nikravesh introduces cross product. So it's a cross product between point 3 SP, okay, point 3, let's just have a look. Point 3 is C in body 1, which is this point over here, okay, multiplied, okay, so SP is, in other words, this vector from the origin of body 1 to point C, okay, and what we're doing here is we're taking the cross product of that with the spring damper force from the tire, and that is added to the external moments acting on body 1. Okay, so that's forces, and then there's obviously weight acting on all the bodies. Alright, then there are no functions that we specify. Joints, let's quickly have a look at the joints. So joint 1 is a revolute joint at point A. Okay, so it's between point index 1 and point index 7. Okay, and it's actually labeled here in this diagram. You can see here in square brackets, point 1 and point 7. There's a revolute joint Q, and that's between points 5 and 6. And then there's a revolute joint at O, and that is between points 4 and 8. Yes. And then there's a translational joint OB. Okay, so it is unit vector index 1 and 2. Okay, I'll talk about the unit vectors in a little bit. Let's just discuss the point index. Obviously, that's quite simple. So it is points 2 and 8. Okay, so it's, and that makes sense because it is between O on body 3, which is this point 8, and B on body 1, which is point number or point index 2. Okay, so let's quickly look at the unit vectors. Okay, so there are 2 unit vectors. The first one is on body 1, body index 1, and you then specify the local components of the unit vector. Alright, now in order to do that, I've actually populated it here with the expanded form of the unit vector. Okay, so I've just created a very quick spreadsheet. So I've got the C and eta components of points B and A respectively here, and now we want to find the C and eta components of the vector that starts at B and ends at A. Okay, so if we do the vector loop, then we can say this vector that starts at the origin and ends at B plus this vector that starts at B and ends at A equals the vector that starts at the origin and ends at A. So if we then just reshuffle that equation, it's easy to see that the vector BA equals the vector OA minus OB. Alright, so we can say the C component is simply the C component of A minus the C component of B. Okay, and the same for eta, and we can then calculate the magnitude of this vector by taking square root of the sum of squares plus okay, and now the unit vector is simply this C component divided by the magnitude, and that C component divided by the magnitude. Okay, and these, so what I've done then is I just copied that, pasted that in as unformatted text, and then I copied that expanded form and pasted it here in the MATLAB for both the C and eta components. Alright, so that's how I got that. The unit vector on body 3 is very simple because it only has a c component, which is 1. Okay, it is 1 in the, yeah, it's positive in the c direction. Right, and then the unit vectors are v1 and v2. And if we can just quickly go back, so body I is, in other words, unit vector I is unit vector 1, and P index I is 0.2, okay, which makes sense. Okay, that ties up, okay, because unit vector is on this body 1, and point index I is point number 2, which is also on body 1. Okay, so just keep close track of what the unit vector number is and what the point index is. All right, so we looked at in joints. Okay, let's quickly look at in points. Very simple, it's just the local coordinates of each of these points, and I do like the way that Prof. Nikravesh numbers these points. He uses the letter and the body on which the point is located. Okay, so that's quite easy. All right, and there are how many points are there? 1, 2, 3, 4, 5, 6, 7, 8 points. Okay, 8 points defining this model. Unit vectors we spoke about, and user force we spoke about. Okay, so now we can run the model. We can simulate its dynamic response for 0,4 seconds. Okay, so to do that, we go to the command window, we clear the workspace, we clear the command window, we run DAP. It's McPherson A. Yes, we want to correct the initial conditions. The final time is 0.4 seconds. The reporting time step is 0.005. Okay, we then view the animation, and in order to do that, we type in the word or the abbreviation anim. Press any key to continue. Okay, the exercise then asks us to plot the coordinate and velocity of body 1 or point C versus time. Okay, now in order to do that, let's just have a look. The velocity of body 1 is quite easy. We first must run the post processor. Then we can say plot, and it's T, comma, the coordinate and velocity of body 1. That's quite easy. Okay, so it's R, the coordinate, colon, body 1. So we want 2. Right. So that's the y coordinate of body 1. Okay. And to plot the y velocity is simply RD. Okay, and there you can have a look. Right, and I did copy and paste all these velocities. Point C is the third point in this input file. Okay, so if we want to do that, we say plot T RP, sorry, that must be a comma, RP, and then it's dash the third point, and we want the y coordinate. Sorry, the y coordinate. Close the bracket, and there we go. That's point C, and the velocity is very simple. RPD. There we go. Okay, so this is what I've just demonstrated in Octave. Okay, so yes, so this is now the y coordinate of point C, the command that we just ran. Okay, so if we yeah, I've copied and pasted that graph in here. Okay, and what you see here is then the y coordinate of body 1 versus time. Now they don't correspond exactly to each other, and the reason for that is because here you can see that obviously as this suspension moves, the y coordinate of body 1 and the y coordinate of point C will be different because they are not the same. They are not corresponding points or coinciding points on the same body. Alright, so let's just have a look if we compare the y velocity of point C with the y velocity of body 1. Then there again there's a slight difference, and that is because this body 1 does not only translate in the y direction, it also rotates. So it has a that's why the y components of the velocities of point C and that of body 1, those y components are different. Okay, and that was then exercise 8.3, and that represented the first model of the McPherson suspension system. Let's have a look at the second simulation model of the identical McPherson suspension system. Okay, the individual bodies, defined points and unit vectors for this model are shown in figure 8.7. Alright, so this model consists now of two moving bodies. Okay, body 1 is the same as before, and we've got body 2, the lower arm. Okay, so there's no body 3 in this model. Alright, and we'll just bear with me for a little bit. There are two pin joints, okay, and it's easy to see this is pin joint at point Q on bodies 2 and body 0, and the pin joint at points A on body 2 and body 1. Okay, those are the two pin joints. So there's one revolute translational joint where body 3 from the first model has been combined as a massless link with the pin joint O and the translation joint to form a revolute translational joint. This model yields 6 coordinates, okay, 2 bodies, 3 coordinates each, 2 times 3 is 6, and 5 constraints. Okay, so the 2 pin joints each has 2 constraints, 2 times 2 is 2, and the revolute translational joint has 1 constraint. Okay, so 4 plus 1 equals 5. Now the program constructs a vector between points O and B and another vector between B and A. And then it enforces the two vectors to stay parallel. Alright, so let's quickly have a look at how that gets executed. Alright, exercise 8.4 asks us to review the M files for this model and simulate its dynamic response once again for 0.4 seconds. Okay, so the input file inanimate is exactly the same as before. There's nothing strange, and we know that the limits are indeed correct to animate this multi-body system. Let's look at in bodies. Now we only have two bodies, body 1 and body 2, as we saw over here. Okay, that makes sense with the initial positions and orientations of each body specified, and in the initial positions and orientation of body 1, the mass and moment of inertia of body 1, mass and moment of inertia of body 2, and the initial position and orientation of body 2. Okay, that's okay. In forces are exactly the same as before. So we have a point to point between, I think there might be a difference in the way we specify the point indices. Just have a look there. Okay, so it's obviously now point index 2 and 4. The stiffness, initial length, damping coefficient and actuator forces are exactly the same as before. And then we have a user function again. That's the tire. Okay, so same as before. If we go to user force, this is exactly the same as what we discussed earlier. Okay, so that's forces, functions, nothing there as before. Joints are different. Okay, so we have a revolute joint at A. Okay, point indices 1 and 7. Okay, and we have a revolute joint at Q. Point indices 5 and 6. Okay, that makes sense. And then we've got this revolute translational joint between points O and B. Okay, and so the I point index is point number 2, which is point B. The J point index is point number 4, which is point O on ground. And then the unit vector index is 1. Okay, so let's quickly have a look at the unit vector. Alright, body index is 1 and the components are exactly as before. Okay, so that's fine. Alright. Okay, in points, nothing strange there. You can have a look. There are fewer points here. 1, 2, 3, 4, 5, 6, 7 points now needed here. And not 8 anymore. Okay, we've got fewer bodies and hence we've got fewer points that we need to specify. Alright, and I think that's it. Alright, then let's have a look here. So it says simulate its dynamic response for 0.4 seconds. So let's clear this. Clear the command window. We say DAP. We say McPherson B. Do you want to correct the initial conditions? Yes. Final time 0.4. Reporting time step 0.05. Okay, and then we can animate. Alright, so we then press a key. Okay, we've just looked at the animation, and the exercise then asks us to plot the coordinate and velocity again of body 1 or point C, or both if you like, versus time. Okay, and that's done exactly the same as before. To plot the y coordinate and y velocity of point C, Yeah, so once again, point C is the third point. Okay, so that's where that 3 comes from. Alright, so if we do that, if we say plot T, comma, RP, colon, 3, 2, sorry, we must first run the post processor, then it will work. Here we go. Alright, so it's exactly the same commands, and that's what you see over here on the screen. If we plot the Y component of body 1, okay, that's what you see over here. Now what I want to show you quickly is the fact that these plots correspond exactly to what we had before. Regardless of the fact that we've changed the model, that we've made the model smaller, we get exactly the same response. So the model is still correct. Okay, and that's the point that Nikravesh is trying to show here. Okay, and the same goes for the velocities, exactly the same as before. Alright, so that is the second simulation of the McPherson suspension. So let's look at the third simulation model. Okay, so the individual bodies, defined points and unit vectors for this model are shown in figure 8.8. Okay, so now this model consists of one moving body, just the body 1 that we had before, one revolute joint, okay, which is here between points Q and A, and one revolute translational joint between points O and B, the same as what we had before. Okay, but what is now new and different is that we've got a revolute joint here between points Q and A. Alright, now body 2 from the previous models has been combined with pin joints Q and A as a massless link to form a revolute joint. Okay, and that I just explained in words, in layman terms, a minute ago. Now this model results in 3 coordinates and 2 constraints. Okay, there is a single body, and each body has 3 coordinates. So in other words, we only have 3 coordinates, and 2 constraints. So the revolute joint represents a single constraint, and the revolute translational joint represents another single constraint. Now the program constructs a vector once again between points Q and A and enforces the length of the vector to remain a constant 0.45 meters. Okay, that's how it works. Alright, so let's quickly have a look at exercise 8.5. Okay, so the exercise asks us to review the input M files for this model and simulate its dynamic response once again for 0.4 seconds. So in animate, nothing changed there. The limits for the animation window boundaries are exactly the same as before. In bodies changed. We only have a single body. We specify the body's position and orientation and the mass and moment of inertia. In forces look exactly the same as before. Just take careful note of the point indices, that they are specified correctly. Okay, so point I is 0.2, and this is the point-to-point force that acts on the on body 1. So the point I is 0.2 and point J is 0.4. Then the spring stiffness, initial length, damping coefficient, and actuator forces are exactly the same as before. Then we once again have the user force, which is the tire, with the stiffness, initial undeformed length, and damping coefficient. And we once again have user force as before. Nothing changed here. Okay, and you can go through that in your own time if you prefer to do so. Alright, so that's in forces, and then obviously there's weight acting on the system. There are no functions. In joints changed again. Okay, so joint 1 is now a revolute. Point I is 0.1 and point J is 0.5, and the length of this joint is 0.45 meters. Okay, then the revolute translational joint is the same as before, that we've discussed in more detail just a minute ago. So we once again refer to, well, let's just have a look. Point I is 0.2, point J is 0.4, and the unit vector is number 1. Okay, and that's exactly as before. It's on body 1, and the local coordinates, I've given them here in many significant digits. Okay, just for completeness sake, that's in joints. In points, there are now fewer points, only 1, 2, 3, 4, 5 points. We've got fewer bodies and fewer points. Okay, so that, but in specifying these points, nothing, there's nothing special to it. You just specify the body and the local coordinates of that specific point. And as before, point C is again our third point, so our command at the end, you'll see in a minute, is exactly the same as before when we want to plot the y coordinate and y velocity of this point C. Alright, u vectors we already spoke about, and user force we already spoke about. Okay, so let's clear our workspace, we clear our command window, and we run DAP, and we say McPherson C. Do you want to correct the initial conditions? Yes, I do. What is the final time? 0.4, time step 0.005, and there we go. Okay, then we can say annum. Press any key, and there we go. Okay, the exercise asks us to view the animation and then plot the coordinate and velocity once again of body 1 and or point C. Okay, and the commands are exactly the same as before, so let's quickly just run the post processor, and then we say plot T, and we want RP colon comma, that's 0.3, and it's the y coordinate, and there we go. So there you can see that's the figure that I've copied here. Okay, and the y coordinate of body 1 is simply plot T comma R colon body 1 y coordinate. Okay, let's just see there, that's what it is. Okay, and as before, the point of all of this is to show you that even with this model, the y coordinates the y-coordinate of point C versus time is once again exactly the same as before, as well as the y-coordinate of body 1 versus time. And the same is true for the velocities. Y velocity of point C is the same as before, even though we now only have a single body with two joints, combined joints if you like. The results stay exactly the same. Alright. So that was then the three McPherson suspensions. Okay, and so we looked at the double A arm suspension and the McPherson suspension, and thank you very much for watching.